This is called a Tensegrity structure, and heaps of you have reached out to me recently showing me this amazing structure saying, hey Angus, you have to check it out, you have to try 3D printing one. And I went and saw an amazing video on the Action Lab where he went into great detail how the structure uses tensile strength, not compressive strength, to actually support quite a lot of weight. I thought this would actually be a fantastic opportunity to highlight the advantages of laser cutting over 3D printing. Now, on this channel, I usually 3D print things, I'm mostly known for 3D printing, but when you're designing shapes and objects like this, where you have large parts that can be slotted together, laser cutting is actually a more suitable technology. You'd start off with sheets of material and you cut it into the profiles you need, and then with some clever design, you can slot it together and end up with something like this. But there's actually an awful lot that goes into laser cutting design in terms of the actual CAD approach in the 3D modeling software that you don't really have to think about when you're 3D printing. With 3D printing, you take an STL file and you print it. The slicer pretty much does the rest. However, when it comes to laser cutting, you actually have to do quite a lot in the file preparation before you send it to the laser cutter software to make sure that it actually works. So that's what we're going to cover in this video. Let's get started. So the laser cutter I'm using for this project is the Beambox Pro by Flux. It's a really nice smart laser cutter. It's got a decent build area, or decent cutting area, 50 watt glass laser CO2 tube, so nice cutting power. And it's a really good unit. I've been using it for the last few weeks, and I'll be doing a deep dive review on it in future, but I'll show you how I used it for this project. So when designing for laser cutting, you have to consider a few different things that you would normally not have to consider with 3D printing. 3D printing, you just export an STL and go and print it in the slicer, and everything will kind of handle the rest. With laser cutting, you end up with what's known as a vector format. So we're going to be working with DXF. That's what the Flux software takes very well, and that's just basically lines. And the laser will cut those lines to make the parts. So it's a simple concept, but to design the parts, you have to put a little bit more consideration in. For example, you have to consider the material thickness. We're working here with a design that has it's very simple, 2 parts, but I've used a tab and slot design. So the first thing you need to consider with laser cutting is your material thickness. So we're going to be using acrylic for this design. A few things about acrylic. It laser cuts beautifully. It's cheap. It's easy to get. The problem with it is it's incredibly brittle, and also it kind of stinks when you print it. I'm not a big fan, but it looks good. It's cheap. Laser cuts cleanly. But something that not many people consider is the material thickness of acrylic is actually kind of variable. So when you're designing for laser cutting, you usually use a tab and slot approach where you will have 2 parts, for example, these 2, and they slot into each other, and then you can use a little bit of glue or something to hold them in place, or a friction fit ideally. So you have to make sure the thickness is correct in your design, so when you actually laser cut it, the tabs and slots work together. And as I said, acrylic can be kind of variable. So here I have 2 sheets of acrylic, right? They're both labeled 3mm. So this one says 3, and this one says 3 as well, okay? But check this out, I've got a pair of calipers here. I'm gonna measure this sheet, which is clear acrylic, and that's reading 2.48, 2.5. So it says 3 from the factory. So either they mislabeled it, or so it's actually meant to be 2.5, or it's actually an undersized extruded sheet, because you can get extruded and cast acrylic as well, and that also affects the thickness tolerance. This sheet says 3 as well, and this is coming in at 2.93, right? So a little bit undersized, totally reasonable though. So this sheet is closer to 3 by a lot than this sheet. So before you even do anything, you need to get your material and figure out how thick it is. And to take this into consideration, I've used parameters in Fusion so I can change the thickness and it will update all of my processes. So under modify, you got to change parameters, and you can see here I've got a material thickness user parameter. So I can change this to suit the material I'm going to use. And I think I'll go with the clear material for this one that I'm going to show in the video. So I'm going to go with 2.5 here. And everything gets a little bit thinner because I've used, for example, with this extrude, I've used material thickness here, right? So I haven't put numbers in, I've used my parameters. So that's step number one you have to consider with laser cutting, is that your material thickness can vary quite a lot. So measure your material to inform your design. The next thing about laser cutting is something called Kerf. So when you design for 3D printing, often you will scale parts to be smaller. So you have clearances, because 3D printing parts will often have fairly poor tolerances, maybe 0.1 or so, or 0.2 millimeters clearance needed for parts to be able to fit together. Laser cutting, you imagine you have that laser that is focused to a point, and as it cuts through the material, it actually leaves that material burnt or vaporized away, and actually takes material away, and that's called your laser kerf. So you need to measure that as well, which will inform our export, because we need to compensate for that. Imagine we have this slot here, for example. If that's not compensated for, it will be larger than what we've designed it, and the parts will be floppy and loose in them. So the best way to figure out your kerf, in my opinion, is to cut out a, say, 20 millimeter or so circle, and I usually do a square as well, just to make sure they're both the same. And you want to measure what that actually turns out to be. So I designed it to be 20 millimeters. It's actually coming out at 19.82. So that's the square, and the circle is coming out at, see, 19.7. So the circle is a little bit smaller than the square. So 19.7, 19.82. I'm going to go with 19.8, I think, to get it as close as I can for the different scenarios. So what you want to do is you want to go to your calculator, and you want to enter your 20 minus whatever the number is. I'm going to go 19.8, and then find out what that is, 0.2, and then you divide it by half. So divide it by 2.1. So that's a pretty standard kerf amount for laser cutting, 0.1 millimeters. So we're going to offset the edges by 0.1 and expand the part. So when it comes through the laser burns away that offset, and you end up with a part that's closer to spec. And the thing about this is different materials have different amounts of kerf, which is why the laser, unless it's a really high-end system, generally doesn't try to compensate for it. You want to do it yourself and design the parts to have the kerf required for the material you're using. Now, there's a myriad of ways to do this offset. You can export a DXF from Fusion and then offset it in a different program like Illustrator. You can offset the sketch. So for example, I can select this object, create sketch. I can do a project, for example, so P for project, and then I can do an offset like this, and I can just offset it manually by an amount, for example, 0.1. So you can see there, I can take that new offset line and export that as the DXF. The problem with all of these options, you can even do it in the manufacturing workflow in Fusion, which is incredibly tedious for what we're doing, is they're very time consuming and a real pain in the butt. So luckily there are plugins for Fusion 360, and for simple objects I've found that this one, DXF for laser, is perfectly fine. It works great. You don't have to worry too much about extra settings. It will do one at a time, so if you have heaps of objects, you might want something better. But for what we're doing, it's only two parts. We just copy them twice. It's totally fine. So what I've got here is the base part. And to use this plugin, you just create a sketch. I'm going to make sure I'm just looking at the sketch here. And then you go to create. And then down here, the plugin is Save DXF for laser cutting. You select the face that you're saving. And then I'm going to zoom in a bit here so you can see the kerf offset, which it does for you. It does the outside and inside offsets automatically, which is really good. So I can change my kerf to 0.1 like that, which is what we sort of found out is the best middle ground for now. And then, okay. And then you can just save that off as a DXF and you'll be able to open it up in your laser cutting software. All right, now two more laser cutting tips specifically with acrylic, and that is relieving stress rises. So as I said, acrylic is incredibly brittle. So when it comes to putting stress on it, you want to relieve any points where there might be stress concentrations, and then it'll crack. I've cracked many an acrylic sheet in my day. So let's start with tapping acrylic. You can do it. It totally works. So I've got some tapped holes here. So these holes are designed for M3, and the standard M3 pilot hole is around 2.5, I think, depending. So I just done 2.4 here. It's a little bit tighter. So a standard M3 tap, as long as it's nice and sharp, works totally fine in my case. Larger tap sizes though, you might start running into cracking issues with acrylic, and you might want to go a bit further away from that pilot hole, a bit closer to the final diameter, to allow it to actually get a thread, but you cannot tighten up tapped holes in acrylic much at all. Don't expect to, because they'll just shatter or strip. Not very strong at all. But this is something that I don't see done very often, and this is stress relieving internal corners. So internal sharp corners in acrylic are a perfect example of where you'll have a stress riser and you push something in, there's pressure, and then the parts will crack from that corner. So what you want to do is relieve them, and I do that using a little circle cutout like this. So what I've done here is I've simply drawn on the original slot some circles, and these are just really tiny, 1 millimeter, really small, right? And they just expand out those internal corners to give it a much better spread of that stress. So it's not an internal stress riser. Those sharp corners are a nightmare. It just spreads it out so you can have quite a tight fit without cracking the acrylic if you do something like this. And I know it sort of looks like what you'll see with CNC, where people will go into the corners because they can't get a sharp corner with a cutting bit. But this is for sort of a different purpose. It's really here to relieve stress, because the laser can do sharp corners totally fine. You just don't want that. You don't want those internal sharp corners because you don't want the stress risers. Okay, so here we are in Illustrator, and I've already opened up the base piece, but let me just show you another pitfall for laser cutting, and that is units. Same with STLs actually. People can save in inch, like imperial, or metric, millimeter, or centimeter units. STLs don't really have a built-in unit. DXFs are the same. So when you open them up, it'll ask you what's the scale. And by default in my Illustrator, it's choosing pixels, which is completely incorrect. This is saved as millimeter format because that's what my Fusion set up as. So you need to always make sure your scaling is correct. So scale 1 unit equals 1 millimeter, and then I can open it up in Illustrator like this. And once you have them opened up, you have to be really careful not to manipulate things too much. I'm just going to copy paste this across, because you're now in a land where there's nothing constraining these pieces. You can very easily change their dimensions and mess up the final part. I've done that so many times. I've skewed parts slightly by accident, laser cut them and gone, oh, they don't fit together because I skewed them by a few millimeters. It's very easy to do. Like, just as an example, when you bring them in, like, look, the lines just are all separate, right? So I'm just going to group these bad boys together. So then the next step with laser cutting is nesting. Now, you can do this in the laser software if it allows for it, or you can use very high-end, usually expensive auto nesting software. The reason you want to nest parts is because it saves on material. And this is a good example. So this is how I cut this piece, and you can see how tightly I nested it all. I did mess up the edge where some parts went off the sheet. That's one of my main complaints of the Beambox Pro at the moment, is it doesn't easily allow you to preview your cuts, but we'll see how we go in the review. But you want to make sure you use as much material as possible because this is now waste. So when it comes to nesting, take your time, and you can manipulate in basically all axes. You can rotate parts, you can mirror parts as well. And you can do stuff like this, where you bring parts really close together, not touching generally unless they have a shared line. But nesting is almost an art form in itself when it comes to laser cutting, to get as many parts in as tight area as possible so you don't waste material. So here we are in Beam Studio. This is the software that the Flux laser cutter, the Beambox Pro, uses. You bring a DXF or other vector files into this, and then you can manipulate them. Now, currently, it's really kind of difficult to use to select things and move them around. It's very finicky. I'm not very happy with it. I'm sure they're going to improve it in time. But currently, I would actually probably prefer to nest in something like Illustrator, save the entire thing as a single DXF, and then dump it in here. Now, the reason I've got these two rectangles is because I was an idiot and have used random bits of the acrylic that I'm cutting, so I actually had to mask off areas that I could use for this part. Now, the cool thing is it is Wi-Fi connected to the Beambox Pro, so it will save as an SVG and then send it across. And it does have a camera, but currently I'm not exactly sure how you can preview in this software. It just sort of starts, and if you press start, it will send it across and just start cutting. But regardless, the actual laser cutter itself is, I'm finding, very high quality, and this is acrylic, so you do need some form of extraction. It smells, it's very acrid. So this laser cutter does have an extraction fan and a tube, but I've added to that a very powerful extraction fan, as well as a much longer tube, which then extracts it into the atmosphere. And the really cool thing about laser cutting is just so satisfying. When it's done, you let the fumes extract and then you just pull away your sheet material and the parts just fall away. So now's the fun part. You have to peel that protective film off your acrylic. If you can get acrylic with a plastic protective film, it's much easier. But with the paper, you got to go slowly, and it is satisfying to a degree, but it can take some time to get it off the material. So peel it away, and at this time, the parts still stink. They definitely still have a smell to them. So once you've peeled that film away and you have the parts, they look quite good, but you should give them a wash. I just give them a rinse with some soapy water, and then I dry them off. And that way they don't have that awful sort of burnt smell, and you can start using them for your project. And here you can see that laser cut kerf that I mentioned. You can actually see there's a slight angle to the edges that have been cut with a laser. That's because it's a specific focal point where the laser will start to diverge out from that, and that's why you need the additional kerf that we added. And here I'm just testing to make sure the parts fit together. Ideally, there'll be a really tight friction fit, but I did end up needing a little bit of glue to hold the parts together. So what we need to do now is tap the acrylic. And look, as I said, it's very soft, easy to tap as long as the hole's the right size. So I just chucked it in a cordless drill and went slowly, and you just blow away the excess swarf that forms. And you just have to be careful because it's such a soft material. But yeah, you can tap it. This is an M3 thread, and it does work fine if you're careful. Anyway, now we're going to glue them together, and as I said, I'm going to be using a solvent to weld these together, and I have this sinister looking syringe with a flat top needle. It's not pointed, so it's still sharp, but it's not pointed. It's a flat top tube, very small diameter, designed for basically this, for dispensing of thin liquids. And I'm using acetone, which will actually solvent weld the acrylic together, just like you can use acetone to solvent weld ABS together. But it's not the correct thing to use. Ideally, you should be using a proper acrylic glue, which will probably have some sort of solvent in it, but acetone on its own is very thin, and I did notice with the clear acrylic, you can see here, it actually started to crack it. It actually started crazing as it was bonding, which is a real shame. But hey, you never know if you never try, and it did still bond them very securely, so I could test the M3 threads, they work good, and we can move on to assembling this Tensegrity structure. And for the string to join these parts together, I'm using braid. This is fishing braid, and it's really cool because it's got very low stretch. It's very, very strong. This is a 30-pound test, which is about 13 kilograms or so, 30.6. And that's way more than what we need for this, but it's cheap, and this has an added bonus of being very bright and colorful. It's difficult to cut. You need something very sharp. I actually use a very nice pair of Lindstrom pliers, which will actually cut it cleanly. I just line them up and cut them to a set size, and then put them in those holes and tighten up the screw. And the reason I went to the trouble of tapping in those screws is so that I can put the braid in the holes and then thread the screws in. Now, as I mentioned, M3 as a tap size in acrylic is really just a suggestion of a tap thread. It's not really going to hold much force. But by doing this, I actually lock the thread in place. And it works really well because you can adjust it to get the tension you want, and you pull it out a little bit or sort of relieve some tension, and then tighten the screw back in, and it locks it in place. I have to say, even though I've seen these shapes now and I know how they work after watching videos like the one on Action Lab, having them physically in my hands is almost surreal. They look like, especially the clear one, it just looks like some sort of alien technology because you think there should be magnets keeping it suspended. It looks like it's using magnets, especially the way it bounces, but it doesn't have magnets or anything like that. It's just got these 4 strings in tension that keep the shape and keep its form, which is fascinating. I do hope you found this video useful, especially as I deep dive into the preparation of 3D models for laser cutting compared to 3D printing. As I described, you have to do a lot of things to make sure the parts join together properly, and I am a little bit disappointed that all I have on hand is acetone, and it did craze the clear plastic. It didn't craze the colored acrylic though, which is really interesting. But I do have some proper acrylic glue on order, but delivery currently takes quite a while. So I would recommend using the proper acrylic glue. And if you did enjoy this video on Maker's Muse, then maybe consider subscribing. I will revisit these. I have a plan to stack them. I want to see how high I can go with these Tensegrity structures. If that sounds interesting to you, maybe consider subscribing. But either way, thanks for watching. I look forward to seeing you again very shortly here on Maker's Muse. Catch you later, guys. Bye.